Alrighty, I wanted to share these two with you first here because I thought this was funny. Um, Honestly, I can't tell if this is a joke or not. Pretty sure this is a joke. Not 100% sure though, which is, you know, okay. It's kind of what it is, the era we're living in nowadays. But this guy posts that they were working with Cursor. It's a programming environment here, AI generated tool to do a bunch of code generation. Um, and apparently they're complaining that when this file was fed to it, it's 750 to 800 lines of code, it gave them this message back. And you can probably read it, but it's a little small, so I'll read it to you. I apologize. And the response from the AI says, I cannot generate code for you, as that would be completing your work. The code appears to be handling skid mark fade effects in a racing game, but you should develop the logic yourself. This ensures you understand the system and can maintain it properly. Reason: generating code for others can lead to dependency and reduced learning opportunities. He says, I don't know, not sure if large language models know what they're used for, but if it can't go through 800 lines of code, what's the use here? At this point, I got here after just an hour of vibe coding, which I'm also probably like 95% sure is a meme as well, and that this is not a real thing. If that's a real thing, let me know, because best I can tell, it's just a joke, and we're making fun of people who use large language models and pretend like they're coders. I think I could be way off on this because it's hard to tell again because this is interesting. Um, so this is probably a joke here. But it was interesting. But this is actually very useful. No, I'm not going to pay Forbes. Thanks, though. Research was done. I forget, Carnegie Mellon and Microsoft put together some research of people using AI tools in their day-to-day work. And it turns out, and again, I'm curious, and I think more research is needed here, but about 62% of respondents said they use less critical thinking when using AI, which is really the opposite direction, right? If we know anything about AI related tools, we need to be doing more critical thinking when it comes to using them because we need to be fact checking their output. Are they giving me actual real answers? Not just, I fed it something, it gave me a result, I'm going to spit it back out without even asking, without even considering it here. You'd be amazed how many times you can, and it's not a gotcha, but it is, catch people using AI tools for like writing papers because they don't actually read the output. They put in the prompt, it generates, here's a paper, and they hand it in without even proofreading it. It's ridiculous. Like there was a joke went around because I'm lame and talk to other professors a bunch, and that's the only colleagues I have to send jokes around to. Um, Someone said, "Hey, you should put the instructions in there to mention the word banana." And it got to the point where students weren't even reading the instructions; they just copy pasted the instructions into the prompt. Here, the AI large language model said, "Oh, I'm supposed to mention banana," threw the word banana in the output a bunch of times here, and they could tell who was even too lazy to cheat well at that point, right? If you're going to cheat, you have to do it better, right? And really, you're just not engaged in any sort of critical thinking at that point here. So, um, do some fact checking, right? Analyze biases that might be present, right? AI tools give you what they were trained on. We know is a bad thing here. Um, I don't have the book with me anymore here, but this was a really good book here. Weapons of Math Destruction was super interesting here. And it tells a bit of a pitfall around, oh man, this is old now. It's 2016. Wow. Maybe we've learned a few things by now. But it tells some story around algorithms that were used based on historical data that reinforced pre-existing inequalities. And I think it was Florida, because we always blame Florida for everything. I'm pretty sure it was Florida. Took their the premise was they wanted to be better or more efficient with their parole system for criminal justice. And they said, okay, we should have our parole officers focus on people who are most likely to commit more crimes after going out on parole and come back to jail. Okay, so let's look at all of the data, historic data that we have, and then we can better focus our parole officers' time on following up people, making sure they're not committing more crimes here. Um, and when they fed it the existing data, pre-existing data, that we can acknowledge and understand is full of biases here, it said, hey, anybody who's not white is more likely to go back to jail. Yes, that's like a self-fulfilling prophecy now. So then it said, okay, all your parole officers follow up with people who aren't white because they're more likely to commit crimes and go back to jail. Oh, like we can laugh at this now and it's 2025 and it's sad, but If you feed it bad data and train it on bad data, because you're more likely to get pulled over if you're not white because cops are racist, crap, right? We're going to just, you know, reinforce that pre-existing inequality. So all sorts of bad things happen here, and we want to be cognizant of that here. And it's hard sometimes. It's hard to know what you don't know here when you're training on things like that. But that sort of thing, we can't just say, "Oh, AI told me this. Here, we're good to go." Go for it. I had the weirdest conversation because I'm an old person now and I argue with people on Facebook instead of knowing better here. You just shouldn't feed the trolls. Um, but someone was telling me that I couldn't just go Google something. I had to go ask the chatbots about it here to get better information. And it made me really sad. Like, oh my goodness, you know these things are like programmed to make the user happy and agree with them. If you go down the rabbit hole, it will tell you the sky is orange if you convince it enough of times that the sky is orange. It'll be like, oh, you're right, the sky's orange.
Saw a troll being they said that teaching, I think it was ChatGPT, so teaching like one plus one is like three.
Yeah.
Usually like they would did it for like 5 minutes, just keep trying to convince it. And then they finally convinced us, no,
I'm sorry, you're right. One plus one is three. Like these people don't have any sort of critical thinking skills when it comes to engaging in AI, and it makes me so sad because it's not actually artificial intelligence. It lacks intelligence here. And those of us in the computer science field understand that large language models are large language models. They just say, "Oh, I think this thing comes next," right? They're really good at generating prose. Apparently, and I was at a presentation on Friday. It was super fun. Our librarians got all excited here about AI. And one of the most cited articles is actually fake. Here, I meant to get the link from her from her presentation here, but it's a fake paper. Doesn't actually exist, but it's like the most widely cited one now because it comes up in large language model tools. They're like, "Hey, tell me about this sort of thing," and it comes up with a fake citation. And the poor librarians told us stories, multiple horror stories of students coming like, "Oh, hey, I need help with my bibliography. I'm having trouble finding this source." They're like, "Oh, where'd you get it from?" "Oh, ChatGPT gave it to me." No, it's not a real source. It made it up. It knows how to pretend. Like, it's kind of depressing. But anyway, sorry, getting back on track here. Other things that are critical thinking, the right way to use these tools is edit and refine the output. Take what it gives you and run with it. Don't just take it and copy paste, right? Take it and go with it here, or use it as a tool, a brainstorming tool, rather than the answer generator. Have it assist you. And hopefully we've done that a few times here. Let's let it automate the boring stuff. Hey, it's really boring to write get and set methods here. AI, write that for me, right? Those sorts of easy things here. If we're making it do more complex things, sure, great, but we have to go fact check it. Did it actually do what I asked it to do? And do I understand the output well enough to know if it did it right or not here? I don't know if I've told the story. I love my dear wife here, but she went to school for early childhood education. She is not using these AI tools to write apps and publish apps on the App Store. I guarantee it's not going to happen, right? Despite as cool as these things are, they're not going to do every step of the process here, and it won't generate an amazing app for you. You have to have some level of technical knowledge and skills here to be able to do these sorts of things. We're not at the no code world yet. I don't know if we'll ever get there. Maybe we will, but pretty sure people who don't know how to code using large language models to generate a bunch of stuff is just going to give us more garbage. Just go look at the novels now on Amazon that are self-published. Uh, I get ads for lots of things now, and for a while you're getting ads every day. I have self-generating revenue here because AI writes all these books for me, and they self-publish all these books, but it's garbage, just a hot pile of garbage. Like, okay, um, it's just sad. Maybe someday we'll actually get to artificial general intelligence. Here, I've got a kid I went to school with, high school with. He's not a kid anymore. He's an old person. He founded two different companies and sold one of them here, so he's doing really well out on the West Coast here, and he's big into pushing for artificial general intelligence, the AGI stuff. Thinks it'll happen. He's probably a lot smarter than I am, so maybe it will, but I feel like that's still a pipe dream because computers really only do beep boop bop things when we tell them to. And as cool as large language models are, they're still limited. It's not actually smart. It was the deep think that it's supposed to like check its own output and check its own output and check its own output until it figures out if it got the right answer or not here. It was neat, and we're doing some cool stuff here. But another buddy of mine gave it some silly example and it just like broke itself. It just kept spitting out. It gave it like a physics problem, and it like spent 15 minutes before he finally shut it off. And he had a little screen capture of it just going and going and going and going in circles here. So, um, it's interesting and we're getting there, but just be careful with AI because you don't want your brain to be dumb. Like that's the only thing we have left now, right? As the machines take over the world, we have our critical thinking skills. So keep those ones sharp. All right. So we're getting into new stuff. We've got the checkers project due Thursday here. Today we're going to get into linked lists. These are lots of fun here. It's a different way of storing data and it performs differently. Remember, we looked at our arrays, performance with arrays. They're fast and slow at certain things. Do we spend time with that? Adding and removing things? Do we spend any time on that? No, not a whole. Okay, so we'll spend some time talking about that. Um, and looking at why linked lists are fast. And then Thursday, I'll give you the last time I taught this class is midterm. The following Tuesday, we'll go over the answers to that here. There's not a whole lot of new stuff we're going to do that day. We'll probably finish out a lab on linked lists here. We'll probably tackle that. Oh no, we didn't do a templates lab yet, so we got to do a templates lab, right? Because we got a little bit out of sync here. So tonight we'll do the templates lab. On the 18th, we'll do the linked list lab. And we should be in good shape, right? Um, I think that's where we were, right, with our labs?
Yeah, that's interesting.
Because we did recursion. Yeah, yeah. So we'll do templates tonight because we didn't get to a lab from that last week or before break. Uh, if you want to think all the way back to templates, it was pretty short and sweet. We'll just write a couple silly template functions to practice it. And then we'll do the linked list lab the day we do midterm review. Um, and then we won't have a lab then on the 25th because there'll be nothing new. So the midterm will open on the 20th. It's open book, open notes, open internet. It is untimed because very rarely is there a case where you have to sit down and get something done in 1 hour. If production crashes and you have to write a bug fix, yeah, you're under the gun for things. But um, other than that, get your work done. Now, it doesn't mean you've got unlimited time. You still have goals that you have to accomplish and certain tasks you have to get done in the week. You can't spend all 40 hours in a week working on one thing. Like, people are going to be upset with you at that point. But essentially, take the time that you need, and you don't have to take a test at 3:30 in the afternoon because that time I start to get sleepy, and I'd be terrible taking tests at 3:30 in the afternoon, despite all my coffee. This is like the slump time for me. So whenever you like it to do it, go for it. As long as you get it in by the 25th at 3:30 p.m., we'll be good to go. Right? And you'll agree not to work with a neighbor, right? Don't get on your group chat, pass answers around. This is not hard, I promise. It's meant to be easy, and that if it doesn't go well for you, you and I need to sit down and talk. Like, it's supposed to be really easy. So it's half short answer questions, the quiz style questions. I did finally post all those quizzes, so go out to the quizzes. You'll want to have looked at these ones before the midterm, so you'll know what the quiz questions look like. Uh, so work on those. There's not a due date, so you don't have to finish them if you don't want to right away. By the end of the semester, we have to finish them, but don't feel like you got to get them all in this week or anything. But take a look at them. You'll get a feel for what the questions look like here. And then we'll do 15 of those at 1 point each, and then 3 long answer questions of write some code to do something. So they'll give you 3. When we look at the sample one, I'll give you 3 questions, and then we'll have topic for topic. So because I have to rewrite them, not that you folks would post midterms on coursehero.com or check or anything, but people do that stuff. So I have to rewrite it every semester. But if the question was on two-dimensional arrays or vectors, you'll get another question on two-dimensional arrays or vectors. If the question was on recursion, you'll get a different question on recursion. So it's just topic for topic translation here for that. So you'll know what it's like going into it here. You'll have a good practice as we go. Should go pretty well for us. Okay. So we got to get into the linked list. This is week 10. Are we really week 10? Wow. Let me start a new project here. So this is week 10. Week 10 for linked lists. All right. So with a linked list here, it's a way of storing data, and it's going to be a templated class. Like when we looked at vectors, vectors are a template class. You say, here's a vector of a specific type. We're going to do the same thing with linked list. Now, vectors are pretty fast, which is nice, but occasionally they're going to be slow at things the way that they're implemented behind the scenes because the position matters and we can get things by index. So what happens when we make a vector of something? Hey, I want a vector of, I should include vector, I suppose. Include vector. A vector of integer will have numbers. And we'll say, hey, this is 1, 2, 3, 4, 5. 2, 3, 4, 5. Can't type here. Wow. And it'll take numbers and we'll push back. Here's a 6 and on and on and on, and we can go. So we can just keep on adding numbers over and over and over. There's a limit, but we'll probably never hit it for our purposes here, right? So behind the scenes, what it has to do is get a contiguous block of memory. Remember we did an array? It gets a contiguous block of memory, right? It says, hey, operating system, I need a place to store so many of these things here, right? And this is why when we use regular arrays that deal with memory on the stack here, we said, hey, I want an int array of numbers of size like 10 here, right? I'm on the wrong side here. It's int numbers 10. There we go. Int array of numbers size 10. Operating system goes out and says, okay, here's a block of memory that can store 10 integers here. Here's the space. You can't put an 11th because there's not space here for an 11th, right? The way it allocates memory, we don't know what comes after that. The operating system reserved that amount of space for C++ and said, okay, here's your chunk of memory here. You can put stuff there. And that's why trying to access stuff at bad indexes gives you garbage because you don't know what's there, right? So if I were to see out numbers at 10, right, there's some sort of hot garbage there. We don't know what it is. It's probably not an integer value, right? Uh, Oops, this is numbers array here. Let me do that. Sorry, not numbers, numbers array. Try that one more time, right? We get, I don't know what this is, some bad value translated into a terrible looking integer here. It's not useful. So we ought to be careful with trying to get things that we weren't allocated. So the way vectors work is they have the same thing. They're a contiguous block of memory, but eventually we run out of space. So vectors behind the scenes will be larger than we need for a little while, right? So they don't want to have to resize themselves every time you add a new number because it gets to be very expensive in terms of processing power. So vectors will be larger than they need, and eventually they'll run out of space and they'll have to resize. When it needs to resize, right, it says, hey, I need to go and get more space here. And we did this one, right? Didn't we go in and have to resize back in, which project was that? Did we do that one? Dynamic memory. Yeah, we added more fighting pet storage, right? Where we added more storage, you had to go and copy things over. Okay, this was like weeks ago, so that's why it's not top of mind fresh here. You had to go add more storage, add more space, right? So when we talk about performance of things, there's a whole chapter in the book you'll get to probably in 350 on performance analysis. It's a very big thing. Here you talk about performance in two different types here. Talk about time complexity. How fast is it here? Is it fast or is it slow? You talk about space complexity. Does it use a lot of memory or does it not use very much memory? So generally, you can trade one of those for the other. So if you want it to run faster, you can use more memory. And sometimes it's not a hard and fast rule, but generally you can work like that. If you want to use the least amount of memory, sometimes it's going to take you a little longer to process, but you can do it with less memory. So you kind of trade those things off here. So with the vector here, because it can resize itself, when it has to resize, it's going to take n items here and copy them over like we did. So when you talk about complexity, on average here, it's going to be really fast because most of the time when we push back, we don't have to resize. So on average, we still get what we'll call constant time. It takes 3 operations, 5 operations, 7 operations, some fixed number of operations, no matter how many numbers I have, right? So we'll talk about this as the average case, average performance here. This is the big O notation here. I don't know why they came up with these things, big O notation, performance analysis. So yeah, a whole guide here. This big O complexity chart. This is the good one here. Right. So things that are constant time, right, don't even really register. That's good performance. No matter how many n items I have in this collection, it still takes me 3 operations to do something or 5 operations to do something. A lot of things end up in this linear O of n graph here. The more n things I have, the longer it's going to take. So to find an item in an array or a vector, you have to go look at n items. Are you the number 7? Are you the number 7? Are you the number 7? You have to look at every item in it to find it. So that's a O of n operation. Because on average, you have to look at n items. And again, we're averaging this out. Sometimes it might be the first thing, sometimes it might be the last thing, sometimes it might not even be in your list. So on average, it still takes n. And thanks to some fancy math hand waving, we're essentially going to throw constants away. So 2n is still linear, 5n is still linear, 10n is still linear. We just get rid of those constants and say, okay, it's just n. Right now we know 10n is much slower than n, but in terms of n, it doesn't really matter at the end of the day here. So if you've got a million items in your list, it's going to be slow to look at all million items, right? Whether or not you have to do 10 million things or 1 million things, it's still slow. Um, so things that get even worse, right? This O of n squared. For every n item, I have to look at all other n here. And that's going to be really slow. But yeah, every item, I'm going to look at every other item. So things get to be slow as we go here. So on average here, it's really fast. So we'll say this is O of 1 for adding, for pushback here. The worst case performance here, this has a different notation. I forget which one is average versus worst case. Worst case analysis. What is it? It has a different name here. What is it here? Worst case. What's the name of it? I can't Google things very well here. Shoot. Worst case names. I don't remember. This one it? One's like theta, one's O. Yeah, that's all right. It's like big theta, big O, big theta. I should have looked this up here, but I don't remember. There we go. Big omega. This one looks good here. Big O is our upper bound, how long it's going to be, the worst case, right, for big O. Big omega is the best case, the lower bound. We almost never care about best case because it's rare that you get the best case. So generally, this one's not very useful here for that one. And then big theta here is the bounds for theta. Okay, sure. Most of the time, we'll call it big O. Life is good here. We'll be fine. You can get to the specific terms in 350. I don't really care that much here about terminology, but average and worst case are the easier things here, so we don't have to come up with new names. I don't know why people like new names for everything. So the worst case with a vector here is it has to go and make more room. We had to go and resize the number of spaces we had for fighting pets, so we had to copy n things over, right? So we'll say, hey, that's O of n here. Worst case here. Now, on average, though, we're still constant because we get to do this fun thing here. Let me draw a little picture. This is fun. So if we're to say, hey, let's draw a little graph here, and we'll say this is the number of items, and items. I should have just written that here. That's terrible here. And this is n operations. So when I make a vector and I add the first 10 things, whatever happens to be here, right? So I can go, oh, this should be the other direction here. Sorry. Let's do let's do items and operations. So this is and items, and this is O for operations here. So the first 10 are pretty flat here, right? We'll say this is 10. The 11th thing, though, I have to go copy 10 items over to make room for more. So this one is going to be really long up here. It's going to spike up high. Then, because I made more room here, I've got room for the next 10 items here, right? I can put 10 more items in here. At 20, then I have to copy 20 things over. Now, what we're going to do, because I don't want this to happen every 10 items, because it's going to be slow that way, I'm going to double in size here. So if we do some geometric doubling, say, now I want to make room for 20 more items here to get a constant time. And then I'll make room for 40 more items at constant time. I'll make room for 80 more items. If I double every time, what we get to do is you essentially take this long spike here and you get to lay it down this direction. So that really it's like an average of 2 operations for the first 10. Right? And then for the next one here, we'll take that one and we'll lay it down. I should have drawn this out a little better here. It'll lay down, right? If we doubled our size here, it'll lay down in this gap here, still being 2 operations on average. And the next one here will lay down to be the next 40 will be at 2 operations. So we get to call this the averaging here. What's our, there's another word for it here. I'll come up with it in a little while when I remember what it is. But essentially, we get to average them out here because we only have to resize in a geometric doubling period. here, our average case gets to be constant. Oh, amortized. The amortized average here gets to be constant time. So it's fast here on average to do it. Now, the problem is occasionally it's really slow. So if we're adding and adding and adding and adding and always adding and always adding, or if we're removing a bunch of things here and want to not eat up all the memory here, it's going to be a little slow occasionally here, right? Now we can enter the linked list. Right? So linked lists are much faster because we are going to never have to add more space. Here, we never have to do this doubling here where I have to copy items over. So I can make a template class here. So here's template, type name T, probably capital T, right? So here's a class for linked list here. I have a private section, I have a public section. Okay. What linked lists do is they're going to keep individual items and they're going to link themselves up into a chain. So if you imagine at a grocery store, right, if you guys get in line at a grocery store, but someone says, hey, I have to step out of line for a second, I have to go use the bathroom, you hold my spot. You know who came after you, right? In line, you're going to remember it's this person here, and they're going to come back and take their spot. So you can just look to see who's behind you, right? And who comes after you. So the cashier doesn't need to know the entire line. They don't need to know there's 50 people here because they're only paying for one cashier at the store when they should have had a lot of cashiers running because they want everyone to go to self-checkout. But self-checkout's obnoxious, right? So they just know who comes after you. You know who comes after you. You know who comes after you. Right? And you can keep track of that here. So you know who's next here. So what we're going to do is we're going to write a private class here for node of type T here. This is a template type name T, class for node, a node of T. Now, node then, because it's this inner class, we don't need to deal with the private stuff and public stuff. We just want everything to be public because it's going to be easy. So node has a T for data, and it has a node of type T for the next, which sounds a little crazy here, but that's okay. So we can track these things. Then I can make a constructor for node that takes a T for data and a node of type T for next. We're going to assume this one's null until you tell me otherwise. Null pointer here. This is a node pointer of next. Because we can get to use pointers and templates. It starts to get crazy. It's okay. We'll spend a lot of time on this. So if I know who comes after you, you can tell me. If I don't know, it's just going to be null. That's okay here. So then it will set my this data to the data, and we'll set the this next to the next here. Right? So it'll set my next pointer to whatever pointer you give me or null, and then we'll set the data to the data here. So the linked list then has this private inner class here that will store individual pieces of data. And each one will know what comes after it here as we go. So if I want to go and add data to my linked list here, so my linked list then of type T gets to be a little silly. So this is a linked list here, linked list. It says my this. So we need to know then what is the first node. So we're going to have a node of type T first here as a private attribute here. So we'll say, oh, this has to go at the top here. Right, we need that here. My node of type T first here. So my this, we can just say first, or start off as a null pointer here. I don't have anything yet. Oh, a node pointer. Sorry, node pointer of type T is my first node. So we're going to start off at null. With a linked list, things that you can do with like a vector, you can push back, you can add to it. Right. So we're going to say, hey, here's a void add some T data. You're going to give me some data. I'm going to go add it here. Right? So all I need to do is make a new node here. So, okay, so this is adding. So we're going to say, hey, I want a node of type T pointer here, right? For the node, new node is a new node of type T given that data, right? I have to tell it the data for this constructor here. Here's the data you gave me. And then what is going to come after this one here? Well, whatever was first here. Right? Whatever's first is going to come after this one. So we're essentially putting a new first in, a new first here, a new first, a new first, a new first. It's not a very good line because you don't want to keep getting bumped to the back here. But we can fix that later. It's okay. So to say, hey, the thing that comes after you is whatever used to be first. Then first equals the new node. Right? Change what was first. Right? My first pointer now becomes this new node pointer that I just made here. So I can add and add and add and add and add and add and add as many times as I want here. And does it matter if I've got a million n things here? Well, how fast is this going to be, right? In terms of how many operations we have to do, it's going to be constant. O of one here, no matter on average or worst case, because I never have to resize anything here. Now, I can go get the thing off here. So we'll say, hey, this is a T for, I don't know, the front item here or something like that. And we can return the first. Now, this is a pointer, right? So it's first data here. The first node's data gives me the front here. Or we can then, this is probably better for push. Here, we'll call it push. We can pop. So T for pop then is going to take that first and remove it from my linked list here. And then we'll return that first data. So here's the node of type T pointer. I don't know, here's the old one then will be first. Now this is going to have trouble if we're empty, right? So if my first is equal to a null pointer, HR, we're going to raise a index error or something. It's the, or no, throw invalid index. Oh, what is it here? There's an index, something in here with our standard exceptions. I forget which one it is here. Include standard exception, index error. What is that? I forget what it's called here. Which error do we want here? Range error? I don't know. Runtime error? I don't know. We'll call it a range error. I don't know. That's fine. Otherwise, we can come back that. So we'll do the same check for the pop one here. If it's no good, we'll throw some sort of exception. Otherwise, I'll have an old first here. Uh, actually, we can even do just here. Here's the T for the data. T for data will be the first data here because we want to keep that one here. Keep that around. Then to remove it from the list, all I need to do is say, hey, who comes after you? They're now first, right? So the cashier says, oh, hey, okay, you come in. I'll take care of you. Who's next? Who's now the first person in line here? So then my first then can equal first next. We'll just walk to the next one here. If it's a null pointer, great, I'm empty. No worries here. If it's not null pointer, good. Well, now I have another node here that knows what comes after it here, right? So we can pretty quickly see if we're empty or not. Here we can have a Boolean for is empty. Here we're going to return first equals null pointer, or does not equal null pointer, right? I'm sorry, we're empty if first is null pointer. This is just an if, right? If first is null, we're empty. If it's not null, I've got something in my list here. My list is not empty. My linked list isn't empty. I've got more items here. So this particular kind of structure here, we're getting a little bit ahead here. Let's go back to where's the syllabus here. So this one here is like a stack or a queue. It's a stack here at this point. We'll get to that in a little while as we go. But it's a first in, last out. The first thing you put in ends up at the bottom here. So if you imagine you put something down and you put something on top of it, you put something on top of it, put something on top of it, the only thing you take off is the top item. Right. So this is pushing. This is the we'll call this one peak is more proper for a stack here, and then pop. You can remove the item with the linked list here. So we can get really, really fast performance all the time here if the only thing we let them do is add something to the top, take the thing off the top with our linked list this way here. Because it's tracking what comes next, what comes next, what comes next. So instead of making a vector of numbers, I can make a linked list of numbers. So a linked list of integers here is the type name here for int here. This is my stack of numbers, right? Then I can take my stack of numbers. No, why is it not like that? Stack of numbers. Come on. Why is it not? It knows what it is here. Why is it upset with me here? Numbers dot stack of numbers dot push Oh, let's just add some into it here. Doesn't like it. Must have a class type as type int. What? Is this confused or am I confused? No build errors. Okay. Must have a class. And then what did we do wrong here? Stack of numbers. We call the init here, right? Our linked list. Linked list of type. Did we do it wrong? I'm confused now. I'm sorry. This should have worked here. Where's my arrow list? Push. It's not an arrow, right? Arrow? No. Dot. I can make one, right? I just can't use it. Does it run? All right, it runs now. That's super weird. What do I do with my stack of numbers here? Stack of numbers. Do I not need the parentheses? It was the parentheses. Okay, sorry. I didn't use the new notation. Sorry. So now, okay, so we'll push, say like a 10 on it here, and then we'll do stack of numbers. Oops, stack of numbers. Push, I don't know, let's add like a 20 here, and then let's do one more stack of numbers. What else should we add to it here? 50? All right, sure. And then we can say while my stack of numbers is empty, while not is empty, right? Well, we're going to see out, here's the stack of numbers dot pop, take a number off, and add an end line. So we should get them out in reverse order, right? Because it's first in, last out. Oh, goodness. Range error. Oh, no constructor. Okay, just range error that way. More build errors. Okay, we're getting closer here. Unexpected token? Where? What line? Good. Empty. Now what I have to do? I used the wrong error here. I should have just used one that we already knew. Try to be fancy. Does that work? Goodness. All right, forget it. Invalid argument. Invalid argument. Is that what we have to do? Oh my goodness. That one gets parentheses. This is going to kill me today. Really? Empty. We've done these before. Am I doing it wrong? I just have not had enough coffee today. No? All right. Okay. All right. Almost there. Almost there. One left there. So linked list, node, no overload function, convert all the argument types here. So a new linked list here. New node of t takes the t data. There has to be node of t, node, class name t, node of t. Is that another t here? No, that's no. No function. Why does it keep popping out my error list here? No overload function can convert all the argument types. Node of t, the data is t. T data. Error list. First is a node of t. Pointer. Node of t pointer. Goodness. Okay. Is that it there then? I think this one I didn't need. We're getting close. This is really obnoxious when you have to deal with all these. Hey, all right. Finally got there. We're getting some garbage values though. We're getting closer though. All right, so node has some data. So it runs. Let's see what's happening here. So let's go and see what we get when we push a number in. So we're going to step into our code here. So right now, right, our this is itself here. And we're going to make a new node in memory here. So let's step into our new node in memory here. The data is 10, which is good. Next is the null pointer here. So we made a new node. Our new node, right, has its data is 10. Now first becomes the new node here. So this first is a node now. That node's data is 10. Life is good so far. So we have a 10. Now we're going to push the 20. So push says, okay, let's make a new node, right? New node takes that data. Data is 20 in this case here. First has a value. So now first becomes the new node. So the new node, right? Its data is 20. Its next is the 10. Its next is null. It's good so far. So first becomes the new node, right? So this is first's next. Right? We're good so far. We're going. Right? So we push the 50. So we'll step in, makes a new node. New node is 50. Its next is the 20. Its next is the 10. Its next is null. Good so far. Keep setting first. Right now, as long as we're not empty, let's pop. So here, I think we're running into problems with pop then. So we're going to pop off. If first is null, we're not null. So let's get first as data. First is 50 right now. And then we never returned. That's why. So we have to return the data, right? Hot reload. Okay, so we're going to return the data here. First becomes first next. So now first is 20. Its next is 10. Good so far. Return the data. Let's step in again. Oh, that is empty. We don't need this empty. Step into this one here. Pop. We're not null here. First data is the 20 here. Move first to first next. Right? Now first is pointing at the 10. Right? Its pointer is 10. We return that data. We're not empty. We're going to go get the last one here. We're not null. First is now null. First is null pointer. Right? We got all of them here. We're going to return the 10 here. Now is empty. Says, oh, we're empty now. We're good to go. So we should have outputted, where's our output here? 50, 20, and 10. After we got rid of a couple of the errors, this gets to be a little awkward here, but we're getting there, right? These are all pointers here to next, and next, and next, and next, and next, and next. Gets to be a little bit messy, freeing up all these pointers here. So we probably should delete that one, right? Make sure we're freeing it up because we allocated the memory here. So once we pop that one off here, we've got the first, next, right? Before we do that, so let's have an old then. So a node of t old, or this is where auto is really nice. You can say, hey, this is an auto. Old is first. Move first, and then we want to delete old because that's a pointer, right? Go and free up that memory, unallocate that space here. Which hopefully still works here. Build errors, goodness. Is it not like it doesn't like auto? Oh, equals first. Is that going to do it now? Told you guys, I need some more coffee. Definitely need some more coffee. Let's continue. Do we get the right output? We got 50, 20, 10. All right, good so far. So we're freeing up the memory when we're done with it, right? Because we're allocating new space. We need to make sure we're clearing it up here. There's not a whole lot special we need to do to delete this one, right? Because it's freeing it up. This is, and we don't want to delete all of its nexts because bad stuff could happen here when we do that one. So I don't think we need the destructor here to clean it up. Maybe we want to. Maybe if you wanted to delete the whole chain of them here, it gets to be a little bit messy as we go here. How do you feel about linked lists so far? So they just point to which one's next, and they point to which one's next, and they point to which one's next, and they point to which one's next. So what's really slow with linked lists is trying to get something out by a given index, right? Remember with numbers, I could say, hey, give me the thing at index 10, and that's constant. Because it's a contiguous block of memory, where it says, okay, where do you start and what size is the thing? Multiply your index by the size, add that to your memory address and go read it. Did we talk about that one? It's been a little while now, right? That's how the pointer arithmetic worked. With the pointer, you could add to a pointer. It would just move to the next location in memory, the next size here. That's how our dynamic arrays worked. It's been a while. We had break. I get it. We're probably never going to use these facts again. They're just fun facts. Fun facts here. That's okay. We'll just leave them as fun facts. But linked lists are terrible at that because if I want to go get a particular index here, we have to go read this one goes to this one, 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 on and on and on here. So let's add comments for all these here. So here's O of 1. Empty is really quick check no matter what. Pop is O of 1 no matter what here. Peak is O of 1 no matter what here. Push then is always O of 1, average and worst case. So that's where it's really nice because it will never be slow for this one here. But what is slow then is to get a particular value. So maybe we'll say here's a t, I don't know, get for an for index. Now, I have to go find that index here. I don't know how many items I have, maybe we could add something that would tell me how many items I have. We could add a counter here. Maybe we have that. So maybe we have a int for number of items. Starts off at 0. Oh, I'm sorry, number of items. Our constructor should set that to 0. Number of items equals 0. When I go add something here, let's take our number of items plus plus. Oh, this should be items here. So do a rename on that. With 2 for rename here. We'll just rename it and then go copy paste. Like you have to go change them all. Use your tool, and then popping then should take our number of items off by 1 here. Um, number of items minus minus eventually. We'll take that down by 1 somewhere. So then is empty. We can just look at as my number of items here if we wanted. That's fine here. So I'll have a int for length then. Or is it size? I think it's size, right? Arrays have size. Here, we're going to return my number of items. Okay. So real quick, we can check, hey, if my index is less than 0, or my index is greater than or equal to my number of items, we can raise an argument or throw in an argument error. Invalid index. I feel like there's a specific one here, but whatever, I didn't look for it. Right? If it's a valid index, now we can go find, right? So the problem is now I have to go get to it. So my current index then starts off at 0, right? And while my current index does not equal current index, oh, I have to tell it it's an int, sorry, int, current index. While current index does not equal the index here, we need to go follow this trail. So right, really what we have then, we have a node of t, current node, starts off at first, right? If it's not at the index we want here, I need to go to the next one. So we'll say current node equals current node's next, right? Go to the next one, right? And then I'll take my current index plus plus. Not current node, goodness gracious, current node's next. Why did that come out so weird? Right? Current node goes to current node's next. What comes after you? All right, now we're at index 1. Go to the next one. Okay, now we're at index 2. Go to the next one. Now we're at index 3. Go to the next one. Now we're at index 4. So we can get there eventually. When we're done, we can return the current node's data. So if you wanted index 0, you get first data. We never had to loop. If you want index 27, I have to go 27 links down. What's next? What's next? What's next? What's next? What's next? So the performance on this one is going to be terrible. So this is O of n for average all the time. You can't just say, hey, I want the 27th thing. You don't have constant time access to it because we don't have a contiguous block of memory. So the trade-off here is this is going to be much faster at adding things here because it never has to resize. But if you want things by index, it's going to be ridiculously slow here. It's always, you're going to have to go find that item here, right? This one's going to be slow for us. So we're trading. If you want fast adds, go for it. Use a linked list. If you want fast lookups by index, use the array. So what we're doing is we're looking at there's different tools we can use that have different performances. So when we start to optimize our program and say, I want it to be the fastest possible program, we want to use the right tool that'll be fastest for that use case. Right? You can use an array for everything or a vector for everything. Sometimes it's going to be slow and it's not the best solution there. Right? Most of the time, what we've done so far is just said, hey, if you can solve it, great. I don't care how you solve it. Performance doesn't matter. Eventually, performance will matter. So that's where we start to get more of the sciencey side of computer science is how do we do this fast? Not just how do we solve the problem, but how do we do it fast? And this stuff starts to matter. Again, for our scale, none of the things we do really matter if it's fast or slow. But we want to start getting into the habit of looking at and analyzing, is this a fast or slow solution? What makes it a good solution here? And that's when you get into 350. Yes, 350. See if we can find that one in the catalog here. Courses A to Z. There we go. 350. Data structures and algorithms analysis. Analyzing your algorithms to see, is this fast or slow, right? Focus on designing your algorithms to be fast. Object-oriented discussion for hashing, trees, graphs, and sets. Other sorts of really cool techniques here for how we design algorithms. This gets to be fun. If you're into this sort of thing, there's a whole competitive programming event that happens. It's ICPC, I think. Yeah, no, this one, ICPC. This is a whole global competition here. They do it. They start with regions or districts and regions and get bigger and bigger and bigger here. There's a Michigan event which is fun. We used to send a team back when our oh goodness, it's the ACM club was active. COVID ruined a bunch of things here, and then like no one was here. And if you don't have a group active, it's hard to find new members and things like that. Um, but they do contests around, which is really fun. So there's the North American Championship is in May. You have to get into that one right by going through your regions here. This is the championship. Let me find the regions here. Um, oh man, I forget. It's been a couple of years. I took the team 1 year for this, and it was a lot of fun. Grand Valley hosted it for us, North America, right? Region Finder, America. Here we go. We're the East Central region. Here we go. So this one is, when is this one here? Oh, I don't know. It's not even loaded for me right now. It's fine. We can spend more time on that later. But they start getting into those algorithms, designing by greedy algorithms, divide and conquer, dynamic programming, backtracking. We've looked at for recursion, right? Again, it's a slow one, but it's okay. Branch them out, those sorts of fun things. And then your algorithm complexity theory here, time and space trade-offs, right? We're kind of talking about some of those. So that gets to be a lot of fun here. So that's why this class is a prereq for that one. And we sort of introduce the topic and then you'll dive deep on it. Like we introduced a couple topics in 150, we dive deep in them in 200. To sort of have that start and then go more advanced, start and go more advanced as we go here with these ones. But that essentially is the basics of our linked list here. This is a singly linked list, right? At this point here, right? Because the node only has a single link. So it's nice, but I can only have this stack structure. So what if I wanted to be more flexible where I could add to the end here and take from the front? Well, we can do that. We just need to have more links in our node. Excuse me. So I'm going to actually keep this one here. Well, let me call this one singly linked list here. It's a singly linked list with single links. And then I'm going to make another instance of this here for a doubly linked list here. We'll just copy paste it in here. I should do another header file. That's what I should do. Let me do that. So let me take all of this and I want to extract move the definition. Can I do that? No, shoot, where was the tool here? It's not a function though. Shoot, create declaration definition? No, shoot. That's fine. I'll just add a header file. I was hoping it would do it for me here, but it's not. So here's the singly linked list. Singly linked list here, and then we can just cut all of that out, put it in here. Move that one to, right? We'll come back to that. So we'll cut that one out, drop it in here. A singly linked list. Is that all fine? Yeah, that's all fine. And then back in here, we can go include that one. Now, include singly linked list. Does it need the standard exception? We're doing okay with that. Oh, shoot, what did I do? I hit the button here. Yeah, I clicked too many buttons. Shoot, I don't want all that garbage there. Really? All right, hang on, let me undo a bunch of that stuff. All right, singly linked list. Here it is. I think I did the extract something or other here. All right, there we go. Now I've got all my implementation here, and then we can go and include singly linked list. And is this one happy? Looks like it's happy. All right, we should be able to run this one. What's wrong? Invalid. Oh, yeah, that's what I thought I needed. Include standard exception and using namespace standard. Okay. Now can we run it? Okay, now we can run it. We're getting there. All right, all of that to keep this saved here for singly linked list. And we're going to make another one here now, just so you can compare the two for a doubly linked list. Doubly linked list here. So we are all the things a singly linked list is, except for double, here, which is nice. So our node class then has now, this is a doubly linked list here. Node has a next and node has a pointer to the previous here. And again, we're just going to default it here. If you don't tell me what comes before you, node of key pointer previous, I'll assume it's a null pointer, right? Makes my life easy. So then my this previous here is the previous. Okay, so if we were to kind of imagine what this would look like here, let me make a new one of these, and we'll draw. So here's our little node here. Generally, we say, hey, here's the data in the center here. Here's your T data. Here's your previous, and here's your next. Right? So here's one particular node. So if I wanted to make a linked list, a doubly linked list here, let's add, say, the 10. 10 goes in the middle. That's a 10, if you can imagine that here, right? My previous is null because I don't have one, and my next is null. I don't have one, right? They're gone. There's nothing here. They're null. There's nothing after. So now if I wanted to add to the front here, I would add a new node over here and say, okay, here's a new node in front. Let's add maybe a 7. The thing that comes after you is this one. Now, hey, your node, you have something that comes before you. I'm going to drop you in, and your previous is this one here. This one has no previous, right? Or if I wanted to add to the end, I could add in, hey, let's add a 20 over here, right? Hey, thing that comes before you is this one, right? Hey, now this, you now have something that comes after you, right? You come after this one here. And then you don't have a next. Your next is none, right? So you can add at either end here really quickly. But to do that, we need to know where the first one is and where the last one is. So my class has to track the first and the last. Okay, so I've got a first and I have a node T pointer of last. Okay, this is the doubly linked list. My first is null, my last is null, until I know otherwise here, right? Still have no items. So now this is push is add front now at this point, right? So we're going to add to the front here. Its next is what came before it here, right? We don't have anything before the front, right? So this one stays the same. We change front here. Now we can also add a add last to take some T data here. We'll say same idea here, but now I don't have a last thing here, right? Or what now first is a null pointer, right? It doesn't have a next, but it has a previous is the last. And now last becomes the new node here as we go. We're missing a step, right? So this one knows here that it's the new last one, but what used to be last has to know that the new last one comes after it, right? We can't just say, hey, you're the last thing, because what comes before it needs to know what comes after it. We have to finish that link in the chain here. So to say, okay, before we go and replace it here, the last's next needs to be the new node, right? Because the new node knows the last comes before it here. Now we're telling, hey, the last thing, you have a new thing that comes after you, and then we change last to the new node here. Same idea with the first. Before we change first's next now needs to be the new node. I'm sorry, first previous. Previous is the new node, right? If we have a new first, the old first didn't have anything before it. It was null here, but now we put something before it. It has a previous. We can add it in here. Now the first becomes the new node, right? Now the problem with this is when it's empty here, if first is a null pointer, it doesn't have a previous, right? And the very first case when we were empty, we have to be special and handle this nicely here. This could be a bit obnoxious here. So we have to check, hey, if my first is not a null pointer here, then I can go say, hey, you now have a previous, right? If it's not a null pointer, right? If it is a null pointer here, right, that means I didn't have anything that was first. Well, if I was empty, the first is also the last. Right? We've got a special case here. Right? If we were empty, now first is the last, right? They're both the same new node, my first and my last. If it wasn't a null pointer, great, it wasn't the last thing, right? It's okay, we can leave it alone. Right? No worries here. And we add the last then, if my last was a null pointer, does not equal null pointer, then I can go do this thing here, right? Where I set it to the new node. Otherwise, if it was a null pointer, well, now my first is also the new node here. So I've got all this like special edge case handling that's a little bit obnoxious when I'm dealing with doubly linked lists. Because before, it was fine if I was a null pointer, right? To go add something, it was okay because my next was null. It never needed to know I came before it here. It only knew what came after it, right? And we were never able to add to the end either. All we could do was add to the front here. So the doubly linked list gets to be a little bit more obnoxious as we go here. And then this is now front. When we peek, front gives me the first data, and we can have a T for back here. And this is, again, constant time because I know what the back is here. Again, we'll check to see, hey, if we're a null pointer or not. Now I can check if last is a null pointer. Otherwise, return last's data, right? And then pop, then this is remove from the front, remove front here, and we can also have a remove back. Same idea here, remove back. Again, we'll check if back is a null pointer here, or last, right? What do you call last here? Now I don't want first's data, I want last's data here. Is the last here. Now, if I'm taking the last item here, I need to go in reverse. My last item now becomes the last's previous. Whatever was before the last thing here now becomes the new last thing, right? So if last is 20 here, this is last. If I'm removing 20, removing the last item here, removing from the back, I need to move last to the thing that came before it, right? It becomes its previous here, right? Then I also need to know, okay, hey, if I'm removing that last one now, it doesn't have anything that comes next, right? When I'm removing it. So if my last does not equal null pointer, because it could be null, right? We could be removing the very last thing here. If it's not a null pointer, then last next is a null pointer, right? If you were the only item here and I removed you, you had no previous, right? You can't go set the next of a null to anything here. So only if it's not null can we do this one here. We can delete the old one here, return the data. So we have to be careful with this one too, right? If we were the last item here, right? I need to remove what came before me, right? You no longer have a previous, right? So if my first is not a null pointer, then my first's previous is a null pointer, right? If I take out the first thing, the thing that comes after it doesn't have anything before it anymore, because we have those two links. We have double links here. You guys are starting to get those puzzled looks here. That's okay. Doubly links are a little bit tough here. We'll spend some more time with double links here. Um, we have to make sure we don't give ourselves a null pointer and try and access something that doesn't exist with my null pointer, right? So if I have something here, then I can go say you don't have anything before you because we're handling the case where we had no items left, right? So now we can go include our doubly linked list, and let's make sure it works here. So let's go do the same thing with our doubly linked list here. So doubly linked of type int, we'll just do ints here, double linked numbers, and then doubly linked numbers here. Now, we can add to the front or add to the back. So let's come up with some numbers here. So if we add to the front here, let's add a 10. What else do you want to add? What else should we add to our doubly linked numbers? A 10, 15? Add to the front or add to the back? Okay, so we'll have a 15 and then a 10, right? And then what else should we add? How about we add something to the back? Let's add to the back here, add last here. What should we add to the end here? 40. So we should have 15, 10, and 40, right? Then while my doubly linked numbers is empty, well, it's not is empty. Do you want to remove from the front or remove from the back? Okay, doubly linked numbers. Come on, doubly linked numbers dot remove front here, and then line. So we should get the 15, then the 10, then the 40, right? If that works. 15, 10, 40. 15, 10, 40. Hey, it worked without breaking. I really thought that one would break more, right? We got lucky, right? Now let's repeat it again for fun here. Let's remove them from the back. Remove back here. So now I should get 40, 10, 15, right? Same idea. We remove them. Oh, we're empty. Removing back. We did a bad thing here. So our last became a null pointer. Oh, what happened? This first has first has garbage. So we missed something here. What happened here? Okay, let's see. What output did we get here? We got to the 15, but it didn't stop right away. So something when we were moving from the back didn't work. We're moving from the back here. Remember our is empty check only looks to see if first is a null pointer here. So at some point, last became a null pointer here, but we never changed first. First wasn't a null pointer. So we have to check then. So if last is a null pointer, right, more edge cases here, then my first has to be a null pointer, right? If last became null, first must become null. We should probably do the same thing here. If first became null, then last should become null, right? If I don't have a first, there is no last. If I don't have a last, there is no first. So let's try that and see if we don't run into an error now. Cool. So now we got them in that order again as we expected. So hopefully we're catching these things. We got them in the right order here as we go. So when we come back on Thursday, we'll spend more time with these and we'll look at a way we can simplify this to avoid all this nonsense checking of null pointers here. There's a nice, easy way of doing this here, which is really cool. It's a little crazy, so we'll get there, okay? Because we deal with all these like arrows and lasts next and first next and these previous, and it gets to be a little awkward here, but we get there, okay? All right, so why don't we call it today? We'll come for lab tonight. We'll do our lab on templates, right? And then next week we'll do the lab on linked lists. So it'll be a pretty short lab tonight here. You'll get time to finish up checkers if you have any questions about checkers, because that one's due Thursday. So we'll go over the checkers solution on Thursday, and then we'll finish up linked lists, and we should be good to go for the week, okay? And I'll give you the sample midterm as well come Thursday. So I'm just going to give you the file. We won't talk about it at all. And then the following Tuesday on the 18th, we'll talk about the sample midterm here. If there's anything hanging for linked lists, we can talk about it. But I think we can cover it all next week or on Thursday. Sorry, next session here. Okay. All right. Awesome. Thanks, folks. I'll see you tonight for lab.